Well, hello AP Physics students, Mr. Kirsten here, and tonight's video will be our last video where we talk about our formula sheet here. So the formulas here are just the beginning of our understanding of rotational motion. You might say we're just scratching the surface of our understanding of rotational motion. But these equations are something you'll want to kind of practice and practice until you don't even need to look at this sheet anymore, and you just know it all. So anyway, our last two topics for today are momentum and centripetal acceleration. Okay, so let's talk angular momentum here. All right, so remember linear momentum is mass times velocity, and the reason it's important is it is a conserved quantity. That is to say, when there's no forces external to the system acting on it, momentum will be conserved. Well, guess what? Same is true for angular momentum, right? So angular momentum is rotational inertia times angular velocity, right? Notice the similarities there. And likewise, angular momentum of a system will be conserved so long as there is not a net external torque acting on the system, all right? So being a conserved quantity, we can use that idea to solve problems. This is also a useful concept. We remember that a force is kind of like the rate of changes of momentum. So the change in momentum of a system is equal to the impulse, or the average force times the time. Likewise, the rate of change of a torque is equal to the rate of change of momentum of the system. So for instance, a very large torque will change the angular momentum of a system very quickly. A small torque will change it slowly. So you can kind of think of this as like the impulse equation for angular momentum. Okay, let's see. Formula for centripetal acceleration is linear speed squared divided by radius. Formula for centripetal acceleration in the angular world is omega squared times r. And again, if you use your linear equation for centripetal acceleration and then plug in your formula for the equivalence there, you can actually get to this equation. All right. So those are our equations for angular momentum. Let's problem solve some here. Let me grab my problem. Mr. Kirstens, you have many problems. So our problem for tonight will be problem number 52 here. Let's talk about this a little bit. What is the angular momentum of a 2-kilogram uniform cylindrical grinding wheel of radius 18 centimeters when rotating at 1500 RPMs? And how much torque would be required to stop it in 6 seconds? So let's get out our problem-solving stuff here, and let's get to work. Or at least I think Mr. Kirsten's going to get out his problem-solving stuff. Okay, here we go. Dun, dun, dun. All right, so problem number 8 looks like this. So here's my grinding wheel. It is a disc or a cylinder, and here's what I know. Notice here I went ahead and right away that 18 centimeters, I converted that into meters. So kind of got my diagram here, and just how it kind of becomes second nature in things to convert things into meters to make sure your units are right. I really like converting things to radians. You will never be wrong when you use radians. It's for angular stuff. It's your go-to safe unit. So I'm going to go ahead and convert revolutions per minute (RPM) into radians per second because that's the safe way to do it. Okay, now I did have to look up the formula for the rotational inertia of a disk. And this is not something you would have to memorize. On the AP test, this would be told to you that the formula, that the number out here is 1/2. Notice all of these are mr squared, but they all have kind of different coefficients here that come from different formulas. That is the formula for the rotational inertia of a disk or of a cylinder. So we could go ahead and calculate the rotational inertia of the disk there. Notice the units for rotational inertia are kilograms times meters squared. Okay, so we know our rotational inertia, we know our rotational speed, rotational velocity, so we can figure out our angular momentum. Notice the units here, kilograms times meters squared per second. Remember, whenever you're labeling units, radians is kind of a dimensionless unit, so you don't have to necessarily include that unless you're talking about an angular speed. So yeah, that's our angular momentum of this spinning wheel. All right. Okay, 7.1 kilograms times meters per second squared per second. Now notice the problem didn't implicitly say it, but when in doubt, I just use counterclockwise as the positive direction. So that's why I got a positive number there. Okay, so that is part A. Part B says, what would the torque have to be to get this spinning wheel to come to a stop in 6 seconds? So there's a couple of ways you could do this problem. I know my final angular speed. Oh, let's switch up here. I know my final angular speed would have to be 0 radians per second over 6 seconds. So I could use this equation, right? This is the angular equivalent of V equals V naught plus AT, right? That's the linear, here's the angular. So I could use that equation, solve for alpha, and then plug that equation into F equals ma. Torque equals I times alpha is kind of like your angular equivalent of F equals ma. So that's how I was going to solve the problem. And then I noticed in the book that they did it a little more straightforward. So I thought we should talk about that. So let's scooch this over just a hair here. So we remember in the linear world that a force is something that changes the momentum of an object over time. Likewise, a torque is something that changes the angular momentum of an object over time. So a torque is equal to our rate of change of angular momentum. And I could do it this way, and I would have to do 2 equations, and this way just does 1 equation. So I think that's how I'm going to choose to do this. Notice here, I do get a negative sign here for my answer for my torque of negative 1.2 Newton meters. What does the negative sign here mean? That would mean that while it's spinning counterclockwise here, the torque would have to be in the opposite direction that it's spinning to slow it down. Okay, which makes sense. So when kind of our convention for angular coordinates is just like in math, up counterclockwise is the positive direction, and down this way is the negative direction. So nice work, AP Physics students. For your joke today, I have a joke for you. Hey, what did Abraham Lincoln say when he was accused of a crime? He said, "Hey, I'm innocent." Get it? He's innocent, right? He's innocent. Oh my gosh. So at least That's what he said to the copper. Get it? See, that's what he said to the copper. At least zinc, that's what he said. Because pennies these days actually aren't made out of copper. They're mostly zinc with a copper coating, but that's chemistry. So anyway, nice job, AP Physics students. We'll see you tomorrow.